Hi, this is Dr. Kimberly Everson, and in this video we're going to talk about simple linear regression. In this video I'm going to approach it from a theoretical perspective, trying to understand what it's all about, as opposed to from a how do you do it perspective. I do have on my channel a variety of how do you do regression in specific software videos that you can look at if you're interested in that. But in this video we're focusing on more the background and the theory of simple linear regression. You might remember from algebra when you took it, maybe back in high school or maybe in early college years, graphing a line. Now these lines, equations might look backwards to you. You might remember that y equals mx plus b formula, where we have the slope times x plus the intercept at the end. And I want you to notice here, this is essentially what I've got here, except for that I've reversed the two pieces. So it would be equivalent to y equals b plus mx. In other words, the y-intercept, a place where the line crosses the y-axis, comes first, and the slope times the x comes second. And we do it that way in statistics courses, and so I want you to be aware of that. If you're not familiar with this, you might find a YouTube video that talks about graphing linear equations for algebra, so that you have some background of what the pieces of these particular formulas mean. When you graph a linear equation or a line, there's really several things that can happen. One is they can slope upward from the left to the right, like the first one. It might be flat straight across, and it might slope downwards, okay, from the left to the right. Of course, it could also be a vertical straight line, but that doesn't typically happen in statistics as much, so it's not something we're going to cover here. Essentially, what's important to understand is here we have what's called positive slope. Here we have what's called negative slope. In the middle, we have zero slope or no slope. So if you think about a variable, let's suppose that I have an x variable along this x-axis and a y value up the y-axis. In this first case, what it's saying is as x increases, y increases at some rate or other, okay? And the last one, we find that as x increases, so as we go from left to right, y decreases at some rate, right? And the middle one, we have as x increases, y does not change. And this is going to be a critical distinction in simple linear regression in statistical analyses, because if as x changes, or as x increases, y does not change, it stays essentially the same. Basically what we're saying is x does not predict y. Okay, so no matter what value of x we have, our best prediction of what y could be is this same flat value. So for that reason, what we're often most interested in when we're conducting simple linear regressions is whether or not this slope is flat, is zero. Okay, if the slope is zero, x does not predict y. If it's positive, it predicts y, and if it's negative, it predicts y, but just in a negative direction. So you'll find when we get into analyzing these simple linear regressions, you'll see that what we are really looking at and care about the most is going to be the statistical significance of the slope. In other words, is there statistical evidence that the slope is not zero? The line's not flat, and x does predict y, either in a positive or negative direction. But when we deal with statistics differently than when we deal with algebra, we start off with data that maybe could be represented here in a scatter plot. With simple linear regression, we're dealing with two variables, an x variable and a y variable. Here it's a little fuzzy, but this is education and income. So what we're finding is, in general, as education increases, income increases, but it's not perfect. when we collect data that we analyze for simple linear regressions, it is very rare for the data to fall right on the line like you find in algebra class. It typically may have some sort of a trend. We may find that we can fit a line somewhat through it, but the points will not fall right on the line, okay? And there may be some like this one up here that are far away from that. So what we are trying to do is we're trying to say, does it fit on a line well enough that I can use a linear model or the equation of a line, like I showed back on that first slide, to best predict y from x? Can I use the equation of a line to predict income from years of education? Well, I'm going to be able to do that here. I'll be able to do it, though, obviously with some error. It's not going to be perfect because nobody's, years of education and income relationship. Well, there'll be probably a point or two that randomly happens to fall in the line. But as a group, they will generally not fall in the line. There's always going to be some error in that prediction. But we want to do it the best that we can. And the reason we usually want to do it is we want to understand what the average relationship is between education and income. Okay, for each person it's slightly different, but on average, typically what is the relationship? And you can see here that it's typically a positive increasing relationship. Now, the trick is then to fit some kind of a line through that data. And you see here I've just put two lines, a blue one and an orange one, randomly through the data there. And the question is, which one's the best one? What we can then create an equation from that particular line, whichever one we choose. But it may be one that's even flatter than that. And the question is, what is the best line to put through the data? What is the best way to predict income from education given this data that we have here? Well, it depends on how you define best fitting line, okay? And there might be a variety of ways people could come up with, okay? You might decide, well, what's the average total distance of these points from the lines, but then you have to ask yourself in what direction and so forth. Well, what we typically do is when we have these are the red points, well, those will just represent our data points for this little example here, and the blue represents our regression line that we're fitting, is we will typically measure the distance of all the points from the lines in the vertical direction. Why the vertical direction? Well, that's our y direction. That's the direction we're trying to predict. And so what we're basically saying is, how far is this point from what this line predicts? The line predicts everything would fall right on the line, okay? The line predicts for a x value of 6, this is a different data set here, a y value that would be, around 12-ish or 13, somewhere around there, okay? But we have a data point that has an x of 6 and a y actually of 22. That's quite a far away from that. However, our other points are quite a bit closer. And so you might imagine a situation in which you could fit every possible line there was, do some kind of an infinitely repeated test where you change the line slope and the line intercept over and over again, and each time you do it, you measure how far all of the points are from the line and pick the best one. Well, best one, again, we've got to define exactly by what criteria, okay? And we'll get to that in a minute. Just want to clarify at this point that this distance right here is what we call a residual or an error. Sometimes we use the term error, but it does not err in the sense that we did something wrong or that point did something wrong, the line is wrong. It just means an error in prediction or how far off this line is from an actual real point that we had in our data set. We call and a term that most statisticians maybe like a little better would be residual. And so you'll see that there'll be a residual associated with every single point, an error residual. Okay, so every one of those 6 points. This one will be the biggest residual. This one will be tiny, tiny, and then these ones kind of in the middle. And those values might be positive, okay, or they might be negative, depending on if it's above or below the line, okay? And those residuals, again, or errors, are something we want to be as small as possible. Okay, well, how could we do that? We could, if we were looking at the infinite possibility of all possible lines that could fit through these points, we could say, let's take the line so that the sum of all of these values, okay, is the smallest. Well, that doesn't really work because some of them are positive and some of them are negative, and they'll add up and cancel each other out to 0. So what's another possibility? Well, we could take the absolute value of all of these, of each of these. In other words, just the distance without worrying about whether it's above or low, just make it positive, okay? And add all that up. That is one thing that could be done, and people have played with that. Another thing that could be done is to deal with the fact that we have positive and negative values is we could square each of the values. Squaring a value always makes it positive. If I square all of these distances, I have a whole bunch of positive numbers now that I can add up that won't cancel each other out because they're all positive. Okay, well, it turns out that's what we do. And the reason that we do that is that there's some great mathematical properties, statistical properties. There's some theoretical statistical things that can be done if we do it that way. That doesn't work if we do the absolute value way. So we do the squared. We take the squared distances. So I square each of these distances, add them all up, and I want that sum to be the smallest thing possible. Well, when we square distances, when we square any numbers, funny thing happens is the big, really big ones get really exaggerated. And so one effect of that is things that are really far from the line have a bigger impact on where the line is than some of the other points. So like this point is quite far from the line, will have quite a bigger impact on where the line ends up falling in the end. Okay, and that's just an effect of it that we live with. And maybe it's a good thing, maybe it's not, you know. So essentially, we find what's called the least squares line, and this is what we call it least squares regression. We square each residual, so that length, that number, and sum it all up for each possible line. This is kind of essentially what happens. And we find the line where the sum is the least or the minimum. Practically speaking, we don't have to put in each possible line through it. What we can do is we can use calculus to come up with a formula for what the equation of the line will be in every case, okay? And so using calculus, we've come up with these formulas here. Now, most of you won't have to do things using formulas. You'll probably be using something like software, maybe a graphing calculator at the very least. And what ends up happening is where we fit this line and we fit this AXA plus BX should look familiar. It's kind of like that MX plus B, but just rearranged. This is our intercept A and our slopes are B. And over here I have Y hat instead of Y. And the reason that I have that, often it's written as a Y with a little triangle carrot top thing on the top of it. But I've written out this way because it's a little bit easier to see and to create in PowerPoint. But at any rate, this Y hat basically means my predicted value for Y. What I predict Y to be is going to fit this equation. And the reason it says Y hat and not Y is because the actual Y value from my data set probably doesn't fall right on the line. Like we saw, you know, in any of these examples here, this doesn't fall right on the line. But we have a predicted value for an x of 6 that falls on the line of being 12. The true value is 22. But the line falls through the predicted values. Okay, so that Y hat, that predicted Y fits this, will fall on this line. Okay, we're going to basically put a line through the data. And the way that we do it is using calculus. We come up with the intercept being the average y, the average x, and then this b here. So average y minus b, the slope, times the average x, okay? And the average, the slope is the trickier thing to get. And it uses this complex algebraic formula. We take each x minus the mean of the x times the associated y times the mean of the y. And here you'll notice this is actual y, not y bar. And over this sum as well. And we add all that up. That's complicated. It's all right. Your calculator does it. Your computer does it. Your software does it. But this is where it comes from. And it's derived by minimizing an equation using calculus. Okay. Now, what you need to be aware of is you'll get out of your software. Let's say we've got this third exam score and final exam score. And we're going to predict a final exam score from the third exam score. So that's my y. This is my x. My data here fits fairly close to a line. Sometimes that happens. A lot of times the data doesn't fit as closely. And my software tells me this is my equation of the line. And this is y hat, again, that predicted y hat, equals, this is the y-intercept, plus 4.83x. So this is the line supposedly associated with this situation right here, okay? Now, the reason that it looks like this line would hit way up here is you have to look down here. The x-axis has been cut off, so always pay attention to that kind of thing in graphics. If we were to stretch out this axis so that it went all the way to 0 for the x-axis as well, you would see that this line hits the y-axis actually at negative 173, and I have this particular slope, 4.83. So that's one example of what I might get out of the software when it fit the actual equation. And the way you interpret each of these values is important. Often the intercept may not apply to our situation. So let's take this example, third exam score and final exam score. If you put a 0 in for x, that cancels this part out, and I just have this. That's my y-intercept. My y-intercept is what y would equal if x is 0. So if a person scored 0 on the third exam, they would score negative 173 on the final exam. Obviously, that makes no sense, okay? You cannot score negative 173 on the final exam, hopefully. So why is that showing that as an intercept? Well, the situation is this. I want you to notice the data. The smallest x value in the actual data is really about 65, and the highest is about 75. So my particular data set only included people who scored from 65 to 75 on the third exam. What that means is this equation does not apply to people outside that range. If you try to apply it to people outside that range, you're doing something called extrapolation, and it's not wise. You will come to invalid conclusions. So what it really means is this is the equation of my line, but it only applies to people who are really in that range, okay? So this y-intercept isn't really meaningful, okay? It helps locate the line in space here as far as how high or low it goes vertically, okay? Because see the slope of this line? You could have a line with the same slope that was just above it, parallel to it, or below it, parallel to it, and this is what anchors it to how high or low the line is, okay? So it is still important to have it, but it does not, interpreting this isn't really meaningful in our situation, and a lot of times it isn't. In this particular case, the slope is more meaningful. What it basically means is this, okay? If I take I could pick any value, so I put in a 70 in here, 70 times 4.83, and do this negative 173, I would get the value that falls right about there, so something a little over 150. Okay, that allows me to predict. But also, what's important here is the slope helps me understand if x increases by 1 unit more, I will get 4.83 one more 4.83 in there. Okay, so essentially my predicted final exam score is 4.83 higher each time x increases by 1. So the most important thing we often use in terms of interpretation from this equation is this. If x is increased by 1 unit, y is predicted to increase by 4.83. So if someone scores 1 point higher on the third exam, our best prediction is that they'll score almost 5 points higher on the final exam compared to somebody else, okay? So that's how we're going to interpret those. And you typically get the data out of some kind of output. This is the output you would get for this example out of a calculator. I've highlighted here, it's going to tell you this. The A is the intercept and the B is the slope that I found. And then there's some other values here that become important, and we'll find them in no matter what software we have, hopefully. Basically, there will be a p-value that is a test of this slope. Remember, we talked about the fact that if the slope is 0, x does not predict y. Our best prediction y is the same no matter what x is, so x doesn't predict y. And this is a test of that hypothesis here. And you see a p-value of 0.026, which is less than 0.05, the typical cutoff. So we would say, yes, we can conclude x does predict y for this data set. So that's one thing that we pull out of here, and that p-value comes from this test statistic with 9 degrees of freedom. Okay? And right here, this is the standard error. I'm not going to talk a lot about that, but that goes into creating this these statistics. R, we'll talk about in just a minute, is the correlation, and R squared is called the coefficient of determination. That all comes out of a calculator, but it will also come out of computer software. Okay? So that's what's you're going to get. Now, the statistical test of the slope tests whether or not this slope is really 0. You can here it doesn't look like 0, but the question is whether it's statistically significantly different than 0. The other thing we often want to look at besides whether this slope is non-zero is how close these points are to the line. You can see that if these points are close to the line, when I make a prediction about what someone's final exam score will be from their third exam, then we're going to be more accurate. Okay, we're going to be closer to what really happens, right? In other words, what they really receive will be closer to what we predict if the points tend to be close to the line. Okay, so you can see that happening there. Well, if we look up at this example, no matter what the line is, the points tend to be a little further from the line. So if we try to predict income from education, the truth of what happens won't be as close to what we predict all the time. Okay, so that's something to be aware of. Well, the way that we calculate it is, the way that we examine that is by a measure called R. And R is actually mathematically very closely related to B, the slope here. This is the equation, or one of the ways of formatting, I guess, the equation for R, the correlation coefficient, and it's mathematically related to the slope. Okay, so this will be calculated again in your calculator. Don't freak out about it. Your calculator or your computer will typically calculate it for you, unless you are in a class where the instructor wants you to calculate everything by hand. You're going to just be using software to figure it all out. Okay, and that's called the coefficient R. And R will come out as being between -1 and +1. Okay, so if R is 0, it means that the points are quite far from the line. There's like really no relationship. And in fact, if the R is 0, the slope will also be 0. Okay. If the R is +1, it means there's a very strong relationship. The points are basically right on the line. And if R is +1, there will be a positive slope. If R is -1, it means that the points fit right on the line, but there will be a negative slope. Now, they never fall right on the line. They're typically, R is never really exactly 0 or exactly -1 or 1. It's usually somewhere in between. and how high the value is determines how closely the points fit to the line or how strong the relationship is between the variables. So that's one thing to be aware of, is that R. And you can see up here, we found an R of 0.66, okay? This is how close they are to the line, quite close really. And the correlation coefficient was 0.66, which is quite large. Now, we also often look at R squared. That's called the coefficient of determination, and you literally find it just by squaring R. The reason we do that is because it's a little bit easier to interpret. So let's look at this point. It's really about 0.44 if you round it, okay? That correlation coefficient of determination of 0.44 relates to this example here. And what the coefficient does that makes it more meaningful to interpret is it relates to the variability of the items. Now, if you notice, the final exam score varies for people, right? It tends to be between what, 130 and 100 and 190 or something. You know, it varies what the people have for their final exam score. What the coefficient does is it tells me the percentage of the variability in the final exam score that can be predicted by the third exam score. So people's final exam scores vary, and because the coefficient of determination was 0.44, we can say 44% of the variability in people's final exam scores can be explained or predicted by their third exam score. It's quite a bit, it's almost half, okay? So, you know, you can kind of say that you can, have half the information about what someone's final exam score will be when you know their third exam score. About 44% of the variability on people who respond is explained by this. Or another way of saying it is that the regression line explains 44% of the variability. Okay, so that's what we do with the coefficient of determination, or R squared, which again will generally be in our output and is something that is very helpful to us. And in this case, it's 0.44. Now your R squared will always be smaller than your R. That's mathematically what happens when you square numbers that are smaller than 1. Okay, and it'll always be positive even if the R was negative. And it's again, it's that percentage of variability, and it's a useful measure. So, again, we went through that one already. Now I'm going to go through another example and talk through some other things as we go. This particular example was done in Stata. I left the code up here in case you're a Stata user. Basically, it regressed this sum scale. It uses the Y, a sum of a bunch of like Likert type items, and against H. Now, if you just look at, this is just the scatter plot, it doesn't look like there's a lot going there, right? It looks like if you put a line through that data, it would be pretty much flat, which basically means, when that happens, that H does not predict the score. And this stuff is the output we get, which will do a statistical test of that. I've put the whole output on here just so you can see what it looks like in one particular software. Softwares will give you the same thing typically, or almost the same thing, but just maybe in a different order or slightly formatted differently. In this output, you'll see over here this 117 we're going to look at. I'm just going to skip down because some of these things are more applicable to multiple linear regression. This R squared is that R, this been squared, 0.006. So you can see that's very, very small. It's less than 1. So less than 1% of the variability in this scale score can be explained by a person's age. Not very much. And then when we look at our regression table, I want you to notice this is the, a lot of software in Stata does this, write things this way, which is they write the name of the variable. Where the name of the variable, the x variable, is written is the line that has the slope. And then it'll typically say something like intercept or constant for the other line if you're doing simple linear regression. In Stata, it puts the intercept last. In other softwares, it might put it first, the first row instead of the second row. In other words, these two rows might be reversed in some softwares. It's okay. You just need to learn to use your software, and that's where I have other videos that can help you in various softwares. So here we have the intercept or constant is 58.04. So if I fit a line through this data, that would be the y-intercept. And the slope is just 0.04. That's very small, very close to 0, isn't it? The question is statistically significant can be answered by the values in this row. We don't typically care whether the intercept is statistically significant. We care about the slope. So I come across here, that's my actual slope. That's the standard error of the slope and the t value, t-test statistic, which was used. And this is the p-value right there, 0.399. So quite large. So basically non-statistically significant. So we do not have evidence that the slope is non-zero. In other words, we do not have evidence that age predicts this sum scale. And then there's a confidence interval around the slope and the intercept as well. So that's the typical type of thing that you're going to see in your output. And I like to throw in non-statistically significant from time to time because you see that a lot actually in real life. While textbook exercises often end up statistically significant all the time, that's not really so real life, okay? It doesn't mean you did anything wrong. I see students, they do their dissertations and something's not statistically significant and they think that means that they have a bad dissertation. No, that's not the case. It just happens in real life. Okay, so when you run a simple linear regression, in addition to getting this output and interpreting it, okay, and if this were statistically significant, we could have a line here, and we would say that as age increases by 1 year, this sum scale increases by 0.04 units. It's not statistically significant though, so we typically do not even interpret it. But we do want to check our statistical assumptions. For simple linear regression, these are the things that you need to check. And there are a variety of ways to check these assumptions, okay? I like doing it in a graphical way, and so that's what I'm going to show you. There are some ways using numbers, but I don't particularly like those. However, your instructor may have you use numbers. Normality of residuals is typically found by finding all the residuals. Remember, that's the distance from an actual point to the line. So you'll have as many residuals as you have points or rows in your data set that are included. And then we're going to graph those just using a histogram and look whether it's normally distributed. We are not looking for perfection. We are looking for extreme departures from normality. Okay? Extreme. If it's extremely non-normal, it's probably skewed. Or bimodal, meaning 2 bumps. Okay? Most often what I'd see though is skewed. Okay? And if that is the case, if it is very non-normal, very skewed, basically what it means is the p-values that you were using to make your decision about that slope being statistically significant, that p-value is inaccurate. Okay? So when you decided whether or not that was statistically significant, you are basing that on poor evidence, poor information. And so that's problematic. Okay? Now, what do you do about that? It's probably beyond what you're studying if you're studying simple linear regression, but most often what you do is you do a transformation of either the x or y. Most often what you try is finding the logarithm of either the x or the y, and often that will fix it, particularly if the skewness is the problem. That's just something to have in your head, but you would typically probably get help if you're studying simple linear regression at this point. The other thing you want to do is you want to look at these other assumptions. One is called homoskedasticity. What it basically means is the points are just as close to the line, whether they're at the bottom end or the upper end. And the way we do it is we look at various plots. You can just look at your initial scatter plot to get an idea of it, but I like to use this plot that's called a residuals. This is the residuals distraction versus fitted plot, fitted value plot. And the reason I do that is because it's most useful when we get to multiple linear regression, and so it's a good habit to start looking at that. And it will have the same pattern as your basic scatter XY plot for simple linear regression, just maybe turned a little on its side if there was a line. If there was a linear, slope, a significant slope. That's the word I'm looking for. What I'm basically looking for is I don't see that points tend to be real close to the line at this end and real far at this end, or vice versa. And if it does happen, you will see a triangular, or we often call it a cone or funnel shape, to these points. That's not the case here, and you are looking for something extreme. If by removing one point, by crossing out the one point, you get rid of that funnel or cone shape, then there's not really a funnel or cone shape, okay? Or if just one or two points is making it look like that. It's not, okay? You need to have the whole pattern of all the points look that way, okay? So, no problem here. The next thing we need to look for, and the reason that's problematic is similar to this problem over here. Your p-values will not be accurate if that's the case. Basically, what we're finding is, what you found is that the line fits better for smaller values of x than larger values of x, or vice versa. And again, a transformation of the data sometimes helps. Okay. Linearity is another thing we look for. Basically, we want to make sure that if there is a relationship between the x and y, that relationship is a line, not a curve or something else, okay? And you're looking for something extremely different than a line. Here, if you see like a U shape or an upside down U, that's a curve. If it's very, very clear and obvious, and again, just by moving one or two points out, just like deleting one or two points out, you don't get rid of the curve. You know, taking one or two points out makes the curve vanish. That's not an issue because it's just one or 2 points. You need the whole data set to really reflect that you have something different than linearity. If that's the case, then you're going to be doing something much more advanced in simple linear regression if a curve fits better. And the last thing we're going to look for in this same graph of outliers. An outlier is a point that's way far away. This is a little far away, but I mean something way far away, miles far away. And it has to be far away and in a direction that it actually impacts the equation of the line. If you have an outlier in there, a value that shouldn't be in there, that is far away in certain directions, it will change the whole slope of the line. And when that's the case, you might consider removing that particular point. Okay, we may talk about that more in a minute. Okay, let me just show you example 2 here. In example 2, I'll explain this here. I have as my y variable the same thing I did in the last one, this sum of a scale, so sum of a bunch of items. But I have as my x variable gender, okay? And this is again a stata example, but it can be done the same way in any. You can do simple linear regression with a binary variable as your x, like gender, okay? When you do it, you typically want to code one of the variables as one of the categories as 0 and the other is 1. So in this case, 0 as male, 1 as female, okay? And it's actually coded here, 1 is male, 2 is female, and that works too, but more often we see 0 as male, 1 as female, okay? And I can go ahead and do that. If, and you're asking, how do I fit a line through this? Well, if these points are down lower and these are up higher, you could put a, if you go to the middle of this set, in the middle of these, you imagine a sloped line going through. Now, in this case, that's slightly true. The females, the group 2 here looks slightly higher than the group 1, okay? So you could get a slight line through it, and you will find that we actually do. And we're going to ignore this part. We use that more for multiple linear regression, and a lot of these things over here. Just want you to point out my R squared again is really tiny. It's 0.003. So, if there is a line here, it's not explaining very much of the variability in sum scale. But I'm going to go ahead and show it to you anyway because I want you to see this kind of example. So what we're going to find in this table is the same thing. The first line goes with the slope for the gender x variable, and then the second line is the intercept. You see the intercept's around 58.9 something or other, statistically significant, but we don't care about that. We care about the slope. The slope is about 0.70, and it's not statistically significant. So what we find is basically, no matter which gender you are, our best prediction of your sum scale is the same. Okay, it's very close to 0. And even our estimate here, not statistically significant, not very big. If it were statistically significant, our way of interpreting this would be, okay, if you are 1 higher in gender, in other words, females 2, males 1. So if you're a female instead of male, if you're 1 higher on the gender variable, we predict a 0.7 higher score on the sum scale. Not very much and not statistically significant in this particular case. Okay, and I want to show you we do the same thing with our assumption checks because we need to. Our residuals, again, we're looking for extreme departures from normality, and this is fine. You will find here that we have a problem. I mean, these just look like this, right? I mean, that's not very helpful. Now, when I created this graph, same as when I created this graph, I did something called jitter, J-I-T-T-E-R, because really they would have all fallen in an exact straight line and there would have been points on top of each other, so you couldn't see how many there were. Most softwares, not all, have this option to jitter when that's the case. In other words, if there's a whole bunch of points in an exact straight line and a bunch will be on top of each other, kind of move them a random amount sideways so I can see how many points are there. So I did that on that graph, and I did it on this one as well, so I could see what was happening here. And you will see here that, okay, I'm looking for homoscedasticity. What that would mean is the points are closer to like the 0, they're tighter in on one side than the other side. So if you were to, you could actually draw kind of a funnel or cone shape from one side to the other, and that is not the case here. Linearity would not really apply because you couldn't get a curve shape when you just have, you know, 2 categories like this. You might be able to, if I had a 3rd category, and maybe it came up way up here, and so going through the middle, a line goes like that, and the curves way up. Lack of influential outliers. That might happen if, say, all my data was squished together and then I had one that was way far away and it was changing that regression line or prediction. But it's not the case here. We don't need to worry about that. Okay. What I wanted to point out here was this particular example. I'm basically looking to see, let me go back to this here, whether the sum scale total score differs by gender. You might be thinking, well, wouldn't you just do that with a t-test? Yeah, absolutely, you can do it with a t-test. If you have a simple linear regression, your y variable always needs to be something integral ratio, continuous variable. But if you have a binary variable, 2 categories, yes, you can do a t-test, but you can also do it as a simple linear regression. So I wanted to just show that to you and compare it to you. If I'm doing it as a simple linear regression, I'm asking, does the line have non-zero slope? Line through the middle of that part, and the middle of that part, is it flat? That's the statistical question being asked. Well, if I do a t-test, I'm asking, is the mean here different than the mean here? Can you see that's the same question? It's really asking the same thing. Why would we do it this way? Well, the reason we would do it this way has to do maybe more with multiple regression. With multiple linear regression, we add in several variables, and we might have some of them be something like gender that's binary like this. And it can be more than binary. It can have more categories than that, but then that's technically multiple linear regression, so I'm not going to talk about that here. Okay, so, you know, when I do a t-test comparing the mean of this to the mean of that, whether they're equal, I'm going to look at the p-value down here if it's a 2-tailed p-test, and it's 0.54, which is really close to the p-value I actually got for the simple linear regression slope. But they're not going to be exactly the same because they're not calculating exactly the same way. They're not doing the exact same thing, but you will get the same conclusion, or you should get the same conclusion. Okay. The only times you might not is if it's like really borderline, where your p-value is really close to 0.05 and maybe it's slightly under one, using one of the two and not with the other. But this can be close. Okay, so again, simple linear regression with a binary variable is really the same as a t-test. And I can do well, technically it would be multiple linear regression then with 3 or more categories. That would be the same thing as a one-way ANOVA. It would be a simple, same idea. Okay, another thing I want to bring up is we often use linear equations for prediction. So if this is, say, our equation here, I'm going to put, if I put a 70 in there, I can calculate out what I predict for my y, right? If I put a 20 in there, I can get my predicted y out. But warning, do not do that. I wanted to remind you again of this idea of extrapolation. If my x values are only a certain range, I don't want to do prediction or try to make conclusions about anything that happens outside that range. Because it could be maybe when we get below here, all of a sudden it starts curving down. Something could change dramatically, or if we get above this value, maybe it starts curving up. We don't know. We only know what happens in the range of the data we have, so don't extrapolate. Okay? I'm going to go through another really quick example to show something with outliers. Okay? Here I'm using a different y value. It's just a test score by age for this data set. And you can see by eyeballing this, this does not look like there's a line, right? But you're wrong, that it's statistically significant. Let's go through this. Okay. Up here, my r squared, almost 0.07, that's not a lot, but it means 7% of the variability, or almost 7%, the variability in this score can be predicted or explained by age or by the regression line. Okay, so there's a little bit of prediction happening. Is it statistically significant? We look down here, remember first line, in-state output has to do with slope. Second line has to do with the intercept or constant. In other softwares, it's the other way around. Like SPSS, it's the other way around. The constant or intercept row comes first. We don't care about the constant. We care about the slope. It gives us this actual slope, this negative 0.32. Doesn't seem like a very big number, but if I come over to the p-value, you can see that is definitely statistically significant. 0.04, way below 0.05, which is typically used. And notice this is negative. So if you can imagine here, there is a very slight line that could be fit through here that is slightly downward to the right. Okay, slightly negative slope. And the way we would interpret it is we would say, if someone is 1 year older, we expect them to score about 1/3 of a point lower on this score, on this test of whatever it is, okay? And we can interpret it in that particular case. And again, we're going to check our assumptions, normality residuals. That is a tiny bit skewed, but we only look for something that's really extreme, okay? And then we look at these assumptions over here. Homoscedasticity is the funnel or cone shape. Do not try to start at that point and make a funnel or cone from that. Remember, if you knock out one point, so let's block that out, it's not there. Is it basically, rectangular looking? Yes, it is. So no problem with that. Linearity, I don't see any kind of a curve. It needs to be very clear, very significant. And we want to make sure there's no significant outliers. I have a little bit of an outlier here, but that's really close to that point. Look at the residual. It's close to 0. In other words, that point's really close to the line. It's not going to affect it. But I will show you a case where outliers makes a difference now. I went into this particular data set and I changed one value. So here we go. This is the original data set, just the scatter plot of the age by score. And I changed one value, so it's very different right up here. You see that right there? Okay, and the whole scale of it changed. So that's, this goes to 150, and this one 20 to 100 versus 0 to 150. So you've got to imagine this squished down in your mind to match this one. I guess I could have made those match, but I didn't think of that. And so I've got this outlier point now. Okay, the question is it an influential outlier? Meaning, does it change my results? I've put here the 2 regression results. Okay, let's just look at the slope. Negative 0.32 was the one we just looked at. And now with that outlier point in there, it's negative 0.24 about. And now just above statistical significance. Well, this one's still statistically significant. So because of that outlier, I not only have not quite achieved statistical significance, but I have changed this slope, okay? And sometimes it can be more dramatic than that. The smaller your data set is, the more one outlier will impact, can impact the results, okay? With a huge data set, won't make a difference. I've got 117 here. It did make a little bit of difference. If I had 1,000 or 10,000 points, this one outlier wouldn't have made any difference to my results. Okay. If I had a data set of only 20, it would have made a much bigger, had a bigger impact. But you can see it's made a huge difference going from a p-value 0.004 to 0.068. That's a big difference in my findings. Okay, so if this was what I was doing my report on, I would have to say no, lack of statistically significant, age does not predict score. Well, if I took that point out, now I do have very strong statistical significance. Age does predict score. So it's very important to keep that in mind, that how big a difference outliers can make in a simple linear regression. How do you find out whether an outlier is influential? Well, first of all, you got to decide whether something's possibly an outlier. You can, with simple linear regression, just look at a plot like this and try to pick out that point and be like, okay, that's the one with a score of almost 150, and pick that out of your data set. You can try simply running the analysis with and without that point to see if it makes a difference. If it makes no difference, just leave it in. If it makes a huge difference, then you have a decision to make. Was this a miscoding? Was this typed in wrong, possibly? Was this someone who shouldn't have been in the data set? I had a situation where there was data collected from maybe junior high school students, and one of the teachers took the survey, and so their age came out as 33 or something instead of 13, and so their data didn't make sense. It made sense to just throw that person out because they didn't make sense to my data set. So there's a lot of judgment calls that has to happen. There are some statistical measures that can be used to identify potential outliers. In other words, values, typically ones that they're quite far away from the rest of the data. I believe in the end it's a judgment call. If there's an art to it, and you need to make a decision based on it. In this particular case, I might say, well, this was a score of 149 actually. And what I did is change a 49 to 149 here. I might assume that's not possible for the test. The test only goes up to 100, so obviously that's a typo. I can't just assume it should have been 49. So there's various things I can do throughout the whole point. You just don't include that person in the study. Some people do something called Windsorizing, which is basically takes that 149 and makes it equal to the next largest value in the data set. So if the next largest value set was a 98, then I would change that to a 98. That way you don't throw out altogether. That's another thing people do sometimes with outliers. But you just have to make those decisions about whether or not that particular point should be included or not. Okay. I just wanted to briefly mention sample size in simple linear regression. The rule of thumb is 10 observations per variable. We have only two variables, x and y, which means at least 20. More is better. What's going to happen is it's harder to achieve statistical significance with a smaller sample. The larger the sample is, the more something called statistical power, which is something you learn about in introductory statistics, you have. The easier it is to get statistical significance or find out there's a relationship if there really in fact is one, if you have a larger sample. It's sort of like if you're looking for a rare animal in the forest, the more of the forest you search, the more likely you are to find it, right? If you just search a tiny little area and you don't find it, you can't conclude the animal doesn't exist in the forest. If you search tons and tons of the forest, you're more likely to find the animal if it exists. Same thing. Bigger sample helps. So that's a very rough rule of thumb. To get a little more accurate, there's this calculator that you can use. It can be used for multiple linear regression as well. If you're doing simple linear regression, you just put in where it says number of predictors, you just put 1. And then if you are really an expert in all this or want to be this is the most up-to-date article on the topic. It has a lot of advanced math in it if you really want to come to understand what's going on. I want to just show you really briefly what multiple linear regression is, building on simple linear regression. Simple linear regression here is represented on the left. I have some x variable predictor, some y variable, right? And I have a line that I want to put through them, and then my error residual are these vertical lines. Okay. Now, let's imagine that I have two x's. So the first x is this direction, the second x is this direction, and the y is the vertical direction, and there's that little triangle at the top showing where the point is. Now, I have drawn the actual line in here because otherwise you can't tell where the point is when it's 3 dimensions. You can't tell where it falls relative to the other points. So the actual points are these little triangles at the top, okay? And so if I have two continuous variables as my predictors and an outcome variable, I'm essentially fitting a plane, so think of a flat sheet of paper, through that cloud of points. So if you imagine this misty cloud of points in 3 dimensions, so little grains floating in the air, you're going to fit a plane to do multiple linear regression through that mist of points in such a way that the distance from the point actually to the plane, not to the ground. I have those lines to the ground just so you can kind of tell where the points are. But you're going to have a residual that's that point down to the actual plane, or up to the plane in each case, those residuals, and we're going to minimize the sum of squared residuals again. So that's what happens with multiple linear regression. Now, when we get with higher dimensions beyond, more than 2, it gets into the next higher dimension thing that you can't visualize. We can typically only visualize into like 3 dimensions. There are some exceptions. I wanted to show one. I have x variable here, second x here, second, predictor here. And then I have a third predictor that's binary. And so that third binary predictor might be, male, female, or it might be a treated group and a control group. And that binary, and in that particular case, you can imagine it as 2 planes being fit through the data. So the male plane and the female plane. Okay, so all the males fall in this plane, the females this plane. So you can kind of imagine it that way as a third variable if the third variable is like binary, or you could have 3 groups and have a third plane. Okay, and just to really confuse you a little, if you've got multiple regression and there's an interaction, these planes won't be parallel to each other. So that's just a little preview of the future of something, and that basically means that in this case the males and females, the way they predict the outcome variable depends on what level of one or more of these x's. Okay, and it gets fairly complicated. So that's just an introduction to the future, and I hope this introduction to simple linear regression has been helpful to you. Feel free to look for some of my other videos to see how to do it in particular software, and also go to dresearch.com. I'm beginning to develop some books on various topics, and there should be one there on multiple linear regression within the next few months from the time that I created the video.